then how can I move the charge? How can the bulb glow? Can magnetic field produce electric current? There is no source of current, no source of potential, but the whole show now demands practically how do I change? Immediately, astonishingly, galvanometer showed some deflections. Hello students, this is SD Sir again from the Temple of Excellence, Vidhyaashram, Pre-University College, Mysuru. A new day, a bright start, new chapter, new session, new thoughts of pondering, certain concepts recollected from the previous chapters. What is that new I have from my basket today? A very, very beautiful chapter, interesting chapter, something called as Electromagnetic Induction. In short, what I also call as EMI, Electromagnetic Induction. So my dear students, my session 1 today is to make you all understand what is electromagnetic induction, what is actually the physical meaning of EMI, not the one which we pay to the banks, but the one which will really pinch our thoughts. Electromagnetic induction, and we shall today study two beautiful experiments which will demonstrate the related phenomenon. Now, my first objective is to make you all understand the meaning of the word induce. I don't go still physically into the existence of induction, but textually let us try to understand what does the word induce refer to. Right in June, when the classes start, the students go at a normal pace with academics until they reach January. That acceleration is not seen. Some of them are very lazy. When it is January, the parents induce students to study with all nobbies and lobbies. Pass your second PU with so much of grade, I bribe you with this. So when it is Jan, parents and teachers induce students to study, which means they are giving a property to the students which they did not have initially. That property is induced in students. So my dear friends, the word induce means give some property to a system which it did not possess earlier. For example, artificial radioactivity, inducing radioactivity in lighter elements which they did not possess by birth. When you study radioactivity, or if you have studied the phenomenon earlier, you understand only heavier nuclei, atomic number greater than 84, exhibit radioactivity. But I can also induce radioactivity in lighter elements. So the word induce means you are giving a property to a system, you are inducing a property to a system which it did not possess by birth. And today we are revealing ourselves. We are just pondering to understand the phenomenon of electromagnetic induction. So let us jump into the world of EMI. Now students, in my previous chapter, which was moving charges and magnetism, I understood the unification of electricity and magnetism. A gentleman by name Hans Christian Ørsted unifies the principles of electricity and magnetism. He told, moving electric charges always produce magnetic fields. Very good. Current flowing through any conductor produces magnetic field. Now, the question arose was, is the reverse effect possible? Mr. Ørsted says and proved that electric current produces magnetic field. He dealt with an umpteen number of consequences which unified the principles of electricity and magnetism. Now people started to ask, is the reverse effect possible? Which means, can magnetic field produce electric current? And the answer was yes. Experiments done by Michael Faraday, Joseph Henry proved that electric current is induced. Again, I use the word induced in closed coils. I repeat, electric current is induced in closed coils when they are subjected to changing magnetic fields. Very interesting. The experiment showed that whenever the strength of a magnetic field is changed around closed circuits, closed coils, magnetic fields induce electric currents. And that whole concept is what they formulated as electromagnetic induction. Therefore, the entire chapter is to understand how changing magnetic fields induce electric currents and the consequences of that current induced due to the change of magnetic fields. So we simply study how varying magnetic fields can induce electric currents in closed circuits. Therefore, to begin with, let us try to understand the definition of electromagnetic induction. What actually electromagnetic induction means? Electromagnetic induction. Electric current induced due to changing magnetic fields. Electromagnetic induction. Now, I consider a circuit where I have a small bulb. A circuit where I have a small bulb which is connected to a coil. In turn, a very simple circuit where I have a small bulb, an LED which is connected to a closed coil. Now the whole show for me here is to make this bulb glow. The entire objective for me, activity for me here is to somehow practically make this bulb glow. I have to see that there is some light coming out of this bulb. How is this possible, sir? There is no source of current, no source of potential. Then how can I move the charge? How can the bulb glow? Yes, all my previous classes, my master chapter told, if a charge has to move, there has to be potential. Only when the charge moves, there is current. Here there is no external source, no source of potential. But still, I say, I require the bulb to glow. Still I say, there has to be some current in the circuit. If there has to be current, there has to be EMF. From where will I get all these things? That is where Mr. Faraday and Mr. Henry helps me out. Now what they say is, there is some magnetic flux that is linked with the coil, or some magnetic field strength that is associated with this coil. Faraday and Henry say, don't worry friends, we will help you all to glow the bulb. How? There is some magnetic flux, some magnetic field strength that is linked or associated with the coil. Somehow change this magnetic field, somehow vary the magnetic flux linked with the coil. What is that we have to do? We have to change the magnetic flux that is linked with the coil. We have to vary the magnetic field that is associated with the coil. The moment practically you achieve this, immediately you can see that the bulb starts glowing, which means there is some EMF induced, and this EMF is inducing some current in the circuit. Very clearly, I have used the word induced. Why induced? Initially, there is no EMF in the circuit. Initially, there is no current in the circuit. But from where do I get it? I have changed the magnetic flux linked with this coil. I have changed the magnetic field strength associated with that coil. The moment I do that, there is some EMF induced in the coil, some current induced in the coil, and that phenomenon is called electromagnetic induction. So, what is electromagnetic induction? Phenomenon in which it is a process, a physical process in which an EMF and hence current is induced in a circuit. We are inducing EMF and current in a circuit. How? By changing the magnetic flux linked with it, by changing the magnetic field strength associated with it. And this phenomenon is what I call as electromagnetic induction. So see, beautifully changing magnetic field, changing magnetic flux around a closed coil has induced electric current. And this beautiful phenomenon is what I call as electromagnetic induction. But the whole show now demands practically how do I change the flux linked with the coil. Practically, is it possible to vary magnetic field strength? That has to happen. How can that happen? That is what is demonstrated next by Faraday and Henry. Therefore, we study experiments of Faraday and Henry, which will demonstrate the phenomenon of electromagnetic induction. This is a very important 3-mark question. Many a times asked in the examination. 2 experiments. The first is called Coil magnet experiment, and the second one is called Coil experiment. The Coil magnet experiment and the Coil experiment, which will demonstrate the phenomenon of EMI, electromagnetic induction. So the first experiment I study here is current induced by a magnet. Current induced by a magnet, which is also called Coil magnet experiment, a very famous experiment which clearly demonstrated the phenomenon of EMI. To begin with, there is a circular coil C which is connected to a sensitive galvanometer. C is a coil which is connected to a sensitive galvanometer. Previous session al helkottidini. Why is the galvanometer used? Good. It will detect the presence of current in a circuit. Galvanometer will check the presence of current in a circuit. And when current comes into existence? Only when there is some EMF. So C is a coil which is connected to a sensitive galvanometer. And here is a magnet. This is the north pole of the magnet, and this is the south pole of the magnet. Now initially what do? I keep the magnet at rest. Nowhere the magnet should come into physical contact with this coil. Some distance from the coil I have placed the magnet, and initially they are at rest. Neither the coil is moving nor the magnet. Very clearly, the galvanometer has shown no deflections. Yes, galvanometer is not deflecting. What do I infer? There is no EMF in the circuit, because of which there is no current. Since there is no current flowing through the circuit, galvanometer is not deflecting. Now what I do is, I move the north pole of the magnet towards the coil. Immediately, galvanometer showed deflections indicating the flow of current. Follow clearly. Now what I do is, I will move the north pole of the magnet towards the coil. The north pole of the magnet is moved towards the coil. Be very careful. Still, there is no physical contact between the north pole or the magnet and the coil. I have simply moved the north pole towards the coil. Immediately, astonishingly, galvanometer showed some deflections. Henry and Faraday were amazed. Why? I have simply moved the north pole towards the coil. Immediately, the galvanometer showed some deflections. What does that mean? There has to be some current flowing through the circuit. There has to be some EMF induced in the circuit. Very astonishing. I don't have a source of EMF. I don't have a potential source, but still EMF is induced. Current is induced. How is that this is possible? As you move the north pole towards the coil, there are magnetic field lines associated with the north pole. Magnetic field lines, as you had your electric field lines. These magnetic field lines have disturbed or changed the magnetic field that is linked with this coil. The magnetic field lines coming out of the magnet vary the magnetic flux which is linked with the coil. So automatically magnetic flux around the coil is disturbed. Magnetic field strength around the coil is changed. Therefore, an EMF is induced in the magnet or the coil, and this EMF gives rise to a current which is sensed by this galvanometer. Now what do we do? The north pole of the magnet is taken away from the coil. Initially, the north pole was moved towards the coil. Now the north pole is taken away from the coil. Again, galvanometer showed deflections, but in the opposite direction. It indicated that the effects are the same, but current is flowing in the opposite direction. Again, the magnetic field lines associated with the magnet has changed the flux strength that is linked with the coil. Therefore, EMF and current is induced. Now, when the south pole of the magnet was moved near the coil or away from the coil, now when the south pole of the magnet was moved near the coil or away from the coil, ಈಗ ಸೌತ್ ಪೋಲ್ ಇದೆಯಲ್ಲ ಅದನ್ನ ಕಾಯಿಲ್ ಟುವರ್ಡ್ಸ್ ಮೂವ್ ಮಾಡ್ತೀವಿ ಅಥವಾ ಅವೇ ಮೂವ್ ಮಾಡ್ತೀವಿ. There were deflections in the galvanometer opposite to the directions of the north pole, which means to say either you move the north pole towards or away from the coil, or south pole towards or away from the coil, the magnetic field lines disturbs the magnetic flux here, changes the magnetic flux, and hence EMF and current is induced, demonstrating a beautiful phenomenon of electromagnetic induction. But when the magnet was relatively at rest with respect to the coil, when I did not move the magnet towards the coil or away from the coil, the magnetic flux was not disturbed. There was no change in magnetic field around the coil. No EMF was induced. No current was induced. Which means, if I have to change the magnetic field around this coil, if I have to change the magnetic flux that is linked with the coil, there has to be relative motion between the coil and the magnet. So very clearly I have seen an instant, a situation where current is induced by a magnet. Now we shall understand current induced by current, coil inducing current in another coil. So C1 is a coil connected to a sensitive galvanometer G. What is C1? It is a coil which is connected to a sensitive galvanometer G. C2 is another coil connected to a battery. Now, why do I require a battery here? That is because I want current inducing current in another coil. Very clearly, current induced by current. So current inducing current in another coil. So I require a source of current in the later one. So I have used a battery. When the coil C2 is moved towards C1, C2 is moved towards C1, there is a current flowing through C2. It is connected to a battery, which means there is some magnetic field around C2. This magnetic field will change the magnetic field associated with C1. The magnetic lines of force here will change the magnetic field strength related to C1, and hence EMF and current is induced in C1. The same effect is seen when C1 is moved towards C2. As we move C1 towards C2, galvanometer here deflects, indicating the inducement of EMF and current. But that is not shown if both of them are at rest. Again, to mean there has to be relative motion between the coils for EMF and current. So my dear students, in this session, I've clearly answered a question as to say, can magnetic fields generate electric current? Yes, magnetic fields which vary with respect to time induce electric current in closed circuits. That is what we call as EMI, electromagnetic induction. EMF is induced, current is induced in a closed coil. How? Change the magnetic flux linked with it. And also two beautiful experiments which demonstrated phenomenon of EMI. In my next session, we will study a set of beautiful laws called Faraday's laws, which will substantiate and justify the phenomenon. Until then, thoroughly go through the discussion of this session. Thank you.